The biggest galaxy we've ever found is so immense, your mind will really struggle to grasp its true proportions. This isn't just dramatic language or hyperbole. It's the simple truth about a cosmic leviathan, residing more than 1 billion light-years from us, quietly existing within the darkness of space, holding more stars than you could ever count in countless lifetimes. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. If you're like most of us, you probably think you have a pretty good handle on how big things can get out there. You've seen those images, right, of Jupiter absolutely dwarfing our tiny Earth. You've heard how our Sun could easily contain 1 million Earths within its fiery embrace. Perhaps you've even managed to picture our own Milky Way galaxy, stretching a mind, boggling 100,000 light-years from one edge to the other. But all of that, every single comparison you've ever encountered, becomes almost meaningless when you learn about what astronomers uncovered, hidden in a profoundly distant corner of the universe. This discovery truly redefines what we thought was possible in terms of cosmic scale. Our home, the Milky Way, is what scientists categorize as a barred spiral galaxy. Imagine a vast, luminous pinwheel slowly turning in the cosmic void. It possesses these magnificent, sweeping arms, not solid structures, but rather regions where stars, gas, and dust are more densely packed. These arms gracefully together, all orbiting around a central core where an incredibly massive black hole resides. From one edge to the opposite side, our galaxy spans approximately 100,000 light-years. To truly understand that, imagine if you could somehow travel at the speed of light, which is the fastest anything can move anywhere in our universe. Even at that astonishing velocity, it would still take you a full 100,000 years to traverse from one side of our galaxy to the other. That alone is a concept almost impossible to fully grasp, isn't it? 100,000 years is a time frame longer than modern humans have even existed on this planet. It's a period far exceeding the time since our ancestors first began creating art on cave walls. It stretches beyond the combined duration of every single civilization that has ever risen and fallen here on Earth. Yet, that immense span is merely the breadth of our own, relatively small cosmic neighborhood. The Milky Way plays host to somewhere between 200 billion and 400 billion individual stars. Each of those stars, in turn, might have planets orbiting around them. Those planets could have moons circling them. Countless asteroids tumble through the emptiness, and comets streak across the vast, dark expanse. Our Sun is just a single, ordinary star among those hundreds of billions, quietly located about 26,000 light-years from the galactic center, in a calm area we call the Orion Arm. Our Sun, along with its entire family of planets, is constantly moving around the center of the galaxy at a blistering speed of about 500,000 miles per hour. Even at that incredible pace, our solar system takes roughly 250 million years to complete just one full circuit around the galactic core. Astronomers sometimes refer to this immense period as a cosmic year or a galactic year. Think about it: during the entire era when dinosaurs roamed our Earth, our solar system didn't even manage to complete one full orbit. The last time our Sun was in approximately its current galactic position, the most complex life forms on Earth were simple marine organisms. That's how incredibly vast even our own galaxy truly is. The distances between individual stars in the Milky Way are almost impossibly empty. Our closest stellar neighbor, a small red dwarf star named Proxima Centauri, is situated about 4¼ light-years away. That distance is so enormous that if you were to shrink our Sun down to the size of a single grain of sand, then Proxima Centauri would be another grain of sand, sitting roughly 4 miles away. The space stretching between those two grains of sand would be essentially a void. Just the faintest whisper of gas and dust, and the occasional solitary particle of cosmic radiation would fill that enormous emptiness. This profound lack of density is truly challenging for our minds to comprehend. We live on a densely populated planet, surrounded by billions of other people, sharing space with countless other living organisms. We are accustomed to density, to things being close together, to our world feeling completely full. But step beyond our solar system, and emptiness quickly becomes the norm. Stars are separated by such immense gulfs that the chance of any two of them accidentally colliding is virtually zero. Entire galaxies can pass right through each other without any actual stars ever making contact. Yet somehow, even in all that incredible emptiness, there's enough material out there to create hundreds of billions of stars in our galaxy alone. The gas and dust scattered between stars might be incredibly sparse, but spread across thousands of light years, it eventually adds up to truly enormous amounts of raw material. New stars are actively forming right now within giant molecular clouds scattered throughout the Milky Way. These are regions where gravity has successfully pulled enough gas together for the incredible process of nuclear fusion to finally ignite. Our galaxy is a vibrant place, alive with stellar birth, even as older stars burn out and quietly fade away. When you gaze up at the night sky from a truly dark location, that hazy, ethereal band of light stretching overhead is actually the combined glow of billions upon billions of distant stars within our very own galaxy. Ancient civilizations often thought it resembled milk spilled across the heavens, which is, of course, where our galaxy's name, the Milky Way, originated. For most of human history, we simply assumed that this visible band encompassed everything. We believed our galaxy was the entire universe. Different cultures offered various explanations for that luminous band of light. The ancient Greeks shared tales of milk spilled from the breast of the goddess Hera. The Romans referred to it as the Via Lactea, which translates to the Milky Road. In India, it was seen as the path souls would take on their profound journey to the afterlife. Aboriginal Australians perceived it as a majestic river flowing through the sky. People throughout all of recorded history have looked up at that same celestial band and pondered its true nature. When the first rudimentary telescopes were pointed toward the Milky Way in the 17th century, early observers began to realize that the milky glow actually resolved into countless individual stars. These stars were too faint and too numerous to be seen with the naked eye, but they became visible through the magnifying power of glass lenses. This was the initial hint that our galaxy was far larger and contained vastly more stars than anyone had previously imagined. It wasn't until the 1920s that a groundbreaking astronomer named Edwin Hubble definitively proved that those fuzzy, nebulous smudges people had been observing through their telescopes were in fact entire galaxies themselves. Each one of them contained billions of their own stars, each one impossibly far away from us. That singular discovery fundamentally altered everything we thought we knew about our place in the cosmos. Hubble made this monumental discovery at the Mount Wilson Observatory in California, utilizing what was, at that time, the largest telescope in the world, a reflector with a mirror 100 inches across. He was meticulously observing a specific class of stars known as Cepheids variables within what was then called the Andromeda Nebula. These particular stars pulse in brightness with a remarkably regular period. By carefully measuring their apparent brightness and their pulsation rate, Hubble was able to calculate just how far away they truly were. The outcome was absolutely shocking. The Andromeda Nebula wasn't merely a cloud of gas residing within our own galaxy, as many astronomers had long assumed. It was, instead, roughly 1 million light-years away, far beyond the furthest edges of the Milky Way. It was an entirely separate galaxy, a complete island universe of stars in its own right. Our galaxy was not the entirety of the cosmos. It was simply one galaxy among many, many others. We now know that Hubble's original distance estimate was actually off by approximately a factor of 2. The Andromeda Galaxy is, in fact, about 2 million light-years away, not 1 million. But the fundamental conclusion remained correct: the universe was vastly larger than anyone had ever conceived, absolutely filled with countless galaxies, each one containing billions of stars. Today, our best estimates suggest there are around 2 trillion galaxies in the observable universe. That's a 2 followed by 12 zeros. Each of those galaxies, in turn, contains billions or even trillions of stars. The numbers quickly become so enormous that they completely lose meaning to our human brains. But here's what makes this story particularly interesting: not all galaxies are created equal. Some are tiny dwarf galaxies, possessing just a few billion stars. Others are massive spiral galaxies, much like our own Milky Way or our closest large neighbor, the Andromeda Galaxy. And then, sitting at the absolute extreme end of the scale, there are the true cosmic monsters of the universe. Galaxies so unbelievably enormous that they make our entire Milky Way look like nothing more than a tiny speck of dust, almost lost in an empty warehouse. Graze them, creating these beautiful, curving formations of stars, gas, and dust. All of this material swirls around a central bulge, where an incredibly enormous black hole silently resides. From one far edge to the opposite side, our home galaxy stretches roughly 100,000 light-years. That means if you could somehow travel at the speed of light, which is the absolute fastest anything can move in our universe, it would still take you 100,000 years to cross from one side of our galaxy to the other. Just letting that sink in for a moment reveals how truly impossible that distance is to grasp. 100,000 years is a span of time far longer than modern humans have even existed. It's more time than has passed since we first began to paint images on cave walls. It's longer than every single civilization that has ever risen and fallen on Earth, combined. And yet that is just the width of our own tiny corner of the vast cosmos. The Milky Way is home to somewhere between 200 billion and 400 billion stars. Each of those stars might have planets orbiting around them, moons circling those planets, asteroids tumbling through space, and comets streaking through the void. Our Sun is just one of those hundreds of billions of stars, sitting about 26,000 light-years from the galactic center in a relatively quiet neighborhood we call the Orion Arm. Our Sun and its entire family of planets orbit the center of the galaxy at an impressive speed of about 500,000 miles per hour. Even at that tremendous velocity, it takes our solar system approximately 250 million years to complete a single lap around the galactic core. Astronomers sometimes refer to this incredibly long period as a cosmic year or a galactic year. To put that into perspective, in the entire time that dinosaurs roamed the Earth, our solar system didn't even complete one full orbit. The last time our Sun was in roughly this same position within the galaxy, the most complex life on Earth consisted of simple marine organisms. That's how incredibly vast even our own galaxy truly is. The space between individual stars in the Milky Way is almost unimaginably empty. Our nearest stellar neighbor, a small red dwarf star named Proxima Centauri, is about 4¼ light-years away. That distance is so immense that if you were to shrink the Sun down to the size of a single grain of sand, then Proxima Centauri would be another grain of sand, sitting approximately 4 miles away. The space in between those 2 grains of sand would be essentially a void. Just the faintest wisps of gas and dust, and the occasional particle of cosmic radiation, would fill that enormous emptiness. This profound lack of density is genuinely hard for our minds to wrap around. We live on a crowded planet, surrounded by billions of other people, sharing space with countless other living things. We are accustomed to density, to things being close together, to the world feeling full. But step outside our solar system, and emptiness becomes the rule. Stars are separated by such vast gulfs that the chance of any two of them colliding by accident is essentially zero. In fact, entire galaxies can even pass through each other without any stars actually hitting one another. Yet somehow, even in all that emptiness, there is enough material out there to make hundreds of billions of stars in our galaxy alone. The gas and dust found between stars may be sparse, but spread across thousands of light years, it adds up to enormous amounts of raw material. New stars are forming right now in giant molecular clouds scattered throughout the Milky Way, places where gravity has pulled enough gas together for nuclear fusion to finally ignite. Our galaxy is alive with stellar birth. Even as old stars burn out and eventually die, when you look up at the night sky from a dark location, that hazy band of light stretching overhead is actually the combined glow of billions upon billions of distant stars within our own galaxy. Ancient people thought it looked like spilled milk across the heavens, which is exactly where the name Milky Way comes from. For most of human history, we simply assumed that was everything. We thought our galaxy was the entire universe. Different cultures had different explanations for that luminous band of light. The ancient Greeks told stories of milk spilled from the goddess Hera's breast. The Romans called it the Via Lactea, the Milky Road. In India, it was seen as the path souls take on their journey to the afterlife. Aboriginal Australians saw it as a river in the sky. People throughout history have gazed up at that same band of light and wondered what it might be. When the first telescopes were turned toward the Milky Way in the 17th century, observers began to realize that the milky glow resolved into countless individual stars. These stars were too faint and too numerous to see with the naked eye, but they became visible through the magnifying power of glass lenses. This was the first hint that our galaxy was far larger and contained far more stars than anyone had imagined. It wasn't until the 1920s that an astronomer named Edwin Hubble proved that those fuzzy smudges people had been seeing through telescopes were actually entire galaxies themselves. Each one contained billions of their own stars, each one impossibly far away from us. That discovery completely changed everything we thought we knew about our place in the cosmos. Hubble made this discovery at the Mount Wilson Observatory in California. Using what was then the largest telescope in the world, a reflector with a mirror 100 inches across. He was observing a class of stars called Cepheid variables in what was then known as the Andromeda Nebula. These stars pulse in brightness with a regular period. By carefully measuring their apparent brightness and their pulsation rate, Hubble could calculate how far away they were. The result was absolutely shocking. The Andromeda Nebula was not a cloud of gas within our own galaxy, as many astronomers had assumed. It was roughly 1 million light-years away, far beyond the edges of the Milky Way. It was an entirely separate galaxy, an island universe, of stars in its own right. Our galaxy was not the whole cosmos. It was just one galaxy among many. We now know that Hubble's original distance estimate was off by about a factor of 2. The Andromeda Galaxy is actually about 2 million light-years away, not 1 million. But the basic conclusion was correct. The universe was vastly larger than anyone had imagined, filled with countless galaxies, each containing billions of stars. Today, we estimate that there are around 2 trillion galaxies in the observable universe. 2 trillion. That's a 2 followed by 12 zeros. Each of those galaxies contains billions or even trillions of stars. The numbers become so large that they stop holding true meaning for our human brains. But here's what makes this story particularly interesting: not all galaxies are created equal. Some are tiny dwarf galaxies with just a few billion stars. Others are massive spirals like our Milky Way, or our nearest large neighbor, the Andromeda Galaxy. And then, sitting at the extreme end of the scale, there are the true monsters of the universe. Galaxies so enormous that they make our Milky Way look like nothing more than a speck of dust floating in an empty warehouse. Together, all orbiting around a central bulge where an incredibly enormous black hole silently resides. From one far edge to the opposite side, our home galaxy stretches roughly 100,000 light years. That means if you could somehow travel at the speed of light, which is the absolute fastest anything can move in our universe, it would still take you 100,000 years to cross from one side of our galaxy to the other. Just letting that sink in for a moment reveals how truly impossible that distance is to grasp. 100,000 years is a span of time far longer than modern humans have even existed. It's more time than has passed since we first began to paint images on cave walls. It's longer than every single civilization that has ever risen and fallen on Earth, combined. And yet, that is just the width of our own tiny corner of the vast cosmos. The Milky Way is home to somewhere between 200 billion and 400 billion stars. Each of those stars might have planets orbiting around them, moons circling those planets, asteroids tumbling through space, and comets streaking through the void. Our Sun is just one of those hundreds of billions of stars, quietly located about 26,000 light years from the galactic center in a relatively calm neighborhood we call the Orion Arm. Our Sun and its entire family of planets orbit the center of the galaxy at an impressive speed of about 500,000 miles per hour. Even at that tremendous velocity, it takes our solar system approximately 250 million years to complete a single lap around the galactic core. Astronomers sometimes refer to this incredibly long period as a cosmic year or a galactic year. To put that into perspective, in the entire time that dinosaurs roamed the Earth, our solar system didn't even complete one full orbit. The last time our Sun was in roughly this same position within the galaxy, the most complex life on Earth consisted of simple marine organisms. That's how incredibly vast even our own galaxy truly is. The space between individual stars in the Milky Way is almost unimaginably empty. Our nearest stellar neighbor, a small red dwarf star named Proxima Centauri, is about 4¼ light years away. That distance is so immense that if you were to shrink the Sun down to the size of a single grain of sand, then Proxima Centauri would be another grain of sand sitting approximately 4 miles away. The space in between those two grains of sand would be essentially a void, just the faintest wisps of gas and dust, and the occasional particle of cosmic radiation would fill that enormous emptiness. This profound lack of density is genuinely hard for our minds to wrap around. We live on a crowded planet, surrounded by billions of other people, sharing space with countless other living things. We are accustomed to density, to things being close together, to the world feeling full. But step outside our solar system, and emptiness becomes the rule. Stars are separated by such vast gulfs that the chance of any two of them colliding by accident is essentially zero. In fact, entire galaxies can even pass through each other without any stars actually hitting one another. Yet somehow, even in all that emptiness, there is enough material out there to make hundreds of billions of stars in our galaxy alone. The gas and dust found between stars may be sparse, but spread across thousands of light years, it adds up to enormous amounts of raw material. New stars are forming right now in giant molecular clouds scattered throughout the Milky Way, places where gravity has pulled enough gas together for nuclear fusion to finally ignite. Our galaxy is alive with stellar birth. even as old stars burn out and eventually die. When you look up at the night sky from a dark location, that hazy band of light stretching overhead is actually the combined glow of billions upon billions of distant stars within our own galaxy. Ancient people thought it looked like spilled milk across the heavens, which is exactly where the name Milky Way comes from. For most of human history, we simply assumed that was everything. We thought our galaxy was the entire universe. Different cultures had different explanations for that luminous band of light. The ancient Greeks told stories of milk spilled from the goddess Hera's breast. The Romans called it the Via Lactea, the Milky Road. In India, it was seen as the path souls take on their journey to the afterlife. Aboriginal Australians saw it as a river in the sky. People throughout history have gazed up at that same band of light and wondered what it might be. When the first telescopes were turned toward the Milky Way in the 17th century, observers began to realize that the milky glow resolved into countless individual stars. These stars were too faint and too numerous to see with the naked eye, but they became visible through the magnifying power of glass lenses. This was the first hint that our galaxy was far larger and contained far more stars than anyone had imagined. It wasn't until the 1920s that an astronomer named Edwin Hubble proved that those fuzzy smudges people had been seeing through telescopes were actually entire galaxies themselves. Each one contained billions of their own stars, each one impossibly far away from us. That discovery completely changed everything we thought we knew about our place in the cosmos. Hubble made this discovery at the Mount Wilson Observatory in California, using what was then the largest telescope in the world, a reflector with a mirror 100 inches across. He was observing a class of stars called Cepheid variables in what was then known as the Andromeda Nebula. These stars pulse in brightness with a regular period. By carefully measuring their apparent brightness and their pulsation rate, Hubble could calculate how far away they were. The result was absolutely shocking. The Andromeda Nebula was not a cloud of gas within our own galaxy, as many astronomers had assumed. It was roughly 1 million light-years away, far beyond the edges of the Milky Way. It was an entirely separate galaxy, an island universe, of stars in its own right. Our galaxy was not the whole cosmos. It was just one galaxy among many. We now know that Hubble's original distance estimate was off by about a factor of 2. The Andromeda Galaxy is actually about 2 million light-years away, not 1 million. But the basic conclusion was correct. The universe was vastly larger than anyone had imagined, filled with countless galaxies, each containing billions of stars. Today, we estimate that there are around 2 trillion galaxies in the observable universe. 2 trillion. That's a 2 followed by 12 zeros. Each of those galaxies contains billions or even trillions of stars. The numbers become so large that they stop holding true meaning for our human brains. But here's what makes this story particularly interesting: not all galaxies are created equal. Some are tiny dwarf galaxies with just a few billion stars. Others are massive spirals like our Milky Way or our nearest large neighbor, the Andromeda Galaxy. And then, sitting at the extreme end of the scale, there are the true monsters of the universe. Galaxies so enormous that they make our Milky Way look like nothing more than a speck of dust floating in an empty warehouse. Together, all orbiting around a central bulge, where an incredibly enormous black hole silently resides. From one far edge to the opposite side, our home galaxy stretches roughly 100,000 light-years. That means if you could somehow travel at the speed of light, which is the absolute fastest anything can move in our universe, it would still take you 100,000 years to cross from one side of our galaxy to the other. Just letting that sink in for a moment reveals how truly impossible that distance is to grasp. 100,000 years is a span of time far longer than modern humans have even existed. It's more time than has passed since we first began to paint images on cave walls. It's longer than every single civilization that has ever risen and fallen on Earth, combined. And yet, that is just the width of our own tiny corner of the vast cosmos. The Milky Way is home to somewhere between 200 billion and 400 billion stars. Each of those stars might have planets orbiting around them. Moons circling those planets, asteroids tumbling through space, and comets streaking through the void. Our Sun is just one of those hundreds of billions of stars, quietly located about 26,000 light years from the galactic center in a relatively calm neighborhood we call the Orion Arm. Our Sun and its entire family of planets orbit the center of the galaxy at an impressive speed of about 500,000 miles per hour. Even at that tremendous velocity, it takes our solar system approximately 250 million years to complete a single lap around the galactic core. Astronomers sometimes refer to this incredibly long period as a cosmic year, or a galactic year. To put that into perspective, in the entire time that dinosaurs roamed the Earth, our solar system didn't even complete one full orbit. The last time our Sun was in roughly this same position within the galaxy, the most complex life on Earth consisted of simple marine organisms. That's how incredibly vast even our own galaxy truly is. The space between individual stars in the Milky Way is almost unimaginably empty. Our nearest stellar neighbor, a small red dwarf star named Proxima Centauri, is about 4¼ light years away. That distance is so immense that if you were to shrink the Sun down to the size of a single grain of sand, then Proxima Centauri would be another grain of sand sitting approximately 4 miles away. The space in between those two grains of sand would be essentially a void. Just the faintest wisps of gas and dust, and the occasional particle of cosmic radiation, would fill that enormous emptiness. This profound lack of density is genuinely hard for our minds to wrap around. We live on a crowded planet, surrounded by billions of other people, sharing space with countless other living things. We are accustomed to density, to things being close together, to the world feeling full. But step outside our solar system, and emptiness becomes the rule. Stars are separated by such vast gulfs that the chance of any two of them colliding by accident is essentially zero. In fact, entire galaxies can even pass through each other without any stars actually hitting one another. Yet somehow, even in all that emptiness, there is enough material out there to make hundreds of billions of stars in our galaxy alone. The gas and dust found between stars may be sparse, but spread across thousands of light years, it adds up to enormous amounts of raw material. New stars are forming right now in giant molecular clouds scattered throughout the Milky Way, places where gravity has pulled enough gas together for nuclear fusion to finally ignite. Our galaxy is alive with stellar birth, even as old stars burn out and eventually die. When you look up at the night sky from a dark location, that hazy band of light stretching overhead is actually the combined glow of billions upon billions of distant stars within our own galaxy. Ancient people thought it looked like spilled milk across the heavens, which is exactly where the name Milky Way comes from. For most of human history, we simply assumed that was everything. We thought our galaxy was the entire universe. Different cultures had different explanations for that luminous band of light. The ancient Greeks told stories of milk spilled from the goddess Hera's breast. The Romans called it the Via Lactea, the Milky Road. In India, it was seen as the path souls take on their journey to the afterlife. Aboriginal Australians saw it as a river in the sky. People throughout history have gazed up at that same band of light and wondered what it might be. When the first telescopes were turned toward the Milky Way in the 17th century, observers began to realize that the milky glow resolved into countless individual stars. These stars were too faint and too numerous to see with the naked eye, but they became visible through the magnifying power of glass lenses. This was the first hint that our galaxy was far larger and contained far more stars than anyone had imagined. It wasn't until the 1920s that an astronomer named Edwin Hubble proved that those fuzzy smudges people had been seeing through telescopes were actually entire galaxies themselves. Each one contained billions of their own stars, each one impossibly far away from us. That discovery completely changed everything we thought we knew about our place in the cosmos. Hubble made this discovery at the Mount Wilson Observatory in California, using what was then the largest telescope in the world, a reflector with a mirror 100 inches across. He was observing a class of stars called Cepheid variables in what was then known as the Andromeda Nebula. These stars pulse in brightness with a regular period. By carefully measuring their apparent brightness and their pulsation rate, Hubble could calculate how far away they were. The result was absolutely shocking. The Andromeda Nebula was not a cloud of gas within our own galaxy, as many astronomers had assumed. It was roughly 1 million light-years away, far beyond the edges of the Milky Way. It was an entirely separate galaxy, an island universe, of stars in its own right. Our galaxy was not the whole cosmos. It was just one galaxy among many. We now know that Hubble's original distance estimate was off by about a factor of 2. The Andromeda Galaxy is actually about 2 million light-years away, not 1 million. But the basic conclusion was correct. The universe was vastly larger than anyone had imagined, filled with countless galaxies, each containing billions of stars. Today, we estimate that there are around 2 trillion galaxies in the observable universe. 2 trillion. That's a 2 followed by 12 zeros. Each of those galaxies contains billions or even trillions of stars. The numbers become so large that they stop holding true meaning for our human brains. But here's what makes this story particularly interesting: not all galaxies are created equal. Some are tiny dwarf galaxies with just a few billion stars. Others are massive spirals like our Milky Way or our nearest large neighbor, the Andromeda Galaxy. And then, sitting at the extreme end of the scale, there are the true monsters of the universe. Galaxies so enormous that they make our Milky Way look like nothing more than a speck of dust floating in an empty warehouse. Galaxies come in many different shapes and sizes. You see, the most common type in our nearby universe are these spiral galaxies, much like our own home, with their distinct, beautiful pinwheel arms and relatively flat, rotating disks. These types of galaxies are typically places where new stars are actively being born, with fresh stellar nurseries forming in those gas-rich spiral arms. The stunning structure we observe is maintained by a delicate balance between the rotational motion of the disk and the powerful gravitational pull of all the matter contained within it. Elliptical galaxies represent another major category. Unlike their spiral counterparts, these galaxies don't really have any particular internal structure. They range in shape from nearly perfectly spherical to highly elongated, oval forms, and they are primarily populated by old, reddish stars. Star formation in elliptical galaxies has largely come to a halt, as they've used up most of their available gas supply. Interestingly, the absolute largest galaxies in the universe are almost all elliptical. They typically form through the merger of multiple smaller galaxies over billions of years, a process that strips away their delicate spiral features. There are also irregular galaxies, which, as their name suggests, have no defined shape at all. These often result from intense gravitational interactions with nearby galaxies, which have pulled and distorted their original structures into chaotic forms. The Magellanic Clouds, visible from the southern hemisphere, are excellent examples of irregular galaxies that are currently being affected by the Milky Way's powerful gravity. These celestial wanderers are slowly being stretched and pulled, their forms irrevocably altered by our galaxy's immense tug. Galaxies aren't just scattered randomly throughout space either. They're organized into even larger, more complex structures. Galaxy groups, for instance, typically contain anywhere from a handful to a few dozen individual galaxies. Our very own Milky Way belongs to what we call the local group, which includes about 80 known galaxies, most notably Andromeda and several dozen smaller dwarf galaxies. Galaxy clusters are even larger still, containing hundreds to thousands of galaxies, all bound tightly together by their collective gravity. And the largest structures of all are superclusters. These are truly vast assemblages of galaxy clusters, stretching across hundreds of millions of light years. The particular galaxy I want to tell you about today is one of those absolute cosmic monsters. It goes by the somewhat uninspiring name of IC 1101, which comes from its entry number in a catalog of celestial objects created over a century ago. But please, don't let that dull name fool you for a second. There is absolutely nothing boring about this cosmic giant. IC 1101 sits squarely at the center of a dense cluster of galaxies called Abell 2029, located in the general direction of the constellation Virgo, as seen from our perspective on Earth. When astronomers point their powerful telescopes toward this particular region of the sky, they observe a truly massive collection of galaxies, all bound together by gravity, performing an intricate, slow dance around a common center. And right in the very heart of that cluster, dominating everything around it like a cosmic emperor seated on a throne, sits IC 1101. This galaxy is estimated to be somewhere around 4 to 6 million light years across. Just let that incredible number truly sink in for a moment. Our Milky Way, which already seemed impossibly large when we discussed it, is only about 100,000 light years wide. IC 1101 is, therefore, roughly 40 to 60 times larger than our entire home galaxy. If you could somehow place IC 1101 where our Milky Way currently resides, it wouldn't just engulf our galaxy. It would swallow our entire cosmic neighborhood. The Andromeda galaxy, which is about 2.5 million light years away from us, would suddenly find itself deep inside IC 1101's massive body. The Triangulum galaxy, another close neighbor of ours, would also be consumed as well. All of the dozens of smaller dwarf galaxies that orbit around us, places like the Large Magellanic Cloud and the Small Magellanic Cloud, would simply become tiny, insignificant components of this giant's unbelievably vast structure. But its sheer size is just the beginning of what makes IC 1101 so utterly incredible. This galaxy is estimated to contain approximately 100 trillion stars. 100 trillion. Our Milky Way, by comparison, has maybe 400 billion stars at most. That means IC 1101 possesses roughly 250 times more stars than our entire home galaxy. If you were to start counting stars in IC 1101, counting one star per second without ever stopping, it would take you over 3 million years just to reach 100 trillion. And that's assuming you never slept, never ate, never took a single break of any kind. This number is so vast it transcends human comprehension, painting a picture of a stellar population that is almost beyond belief. The story of how we first stumbled upon this cosmic giant actually begins way back in 1790, when a German-born British astronomer named William Herschel was meticulously scanning the night sky with his telescope. Herschel was one of the greatest astronomers of his era, a true pioneer. He had already famously discovered the planet Uranus several years earlier, and he dedicated much of his life to cataloging thousands of celestial objects that no one had ever documented before. On June 19th of that year, Herschel pointed his telescope toward a specific region of the sky in the constellation Virgo and noticed a faint, fuzzy blob of light. He carefully recorded its position, made a note, and then moved on to the next object in his systematic survey. At the time, Herschel had absolutely no way of knowing what he was truly looking at. The technology simply didn't exist to accurately measure how far away this object was. The scientific understanding hadn't yet evolved to recognize that it was an entire galaxy, completely separate from our own. Herschel simply logged it as another nebula, one of many mysterious, cloud-like objects scattered across the heavens. For over a century, that faint smudge of light remained a profound mystery. It was eventually given the rather technical designation IC 1101 when it was included in a catalog called the Index Catalog, which was a significant expansion of an earlier, more rudimentary list of celestial objects. Astronomers studied it whenever they could, but without the proper tools to truly understand its nature. It remained just another entry in a very long list of cosmic curiosities. Everything fundamentally changed in the 20th century, however, when astronomers developed much better telescopes and groundbreaking new techniques for accurately measuring cosmic distances. They eventually discovered that IC 1101 was not a mere cloud of gas within our own galaxy. It was an entirely separate galaxy mind-bogglingly far away. The light we observe from IC 1101 today actually left that galaxy over 1 billion years ago. It has been journeying through the vast, empty void of space for more than 1 billion years just to reach our powerful telescopes here on Earth. When that ancient light first began its incredible journey toward us, life on Earth was still predominantly composed of single-celled organisms. Complex animals, as we know them, had not yet even begun to evolve. The dinosaurs would not make their appearance for another several 100 million years. Every major event in human history, from the very first civilizations to the invention of the telescope itself, all happened while that ancient light was still relentlessly crossing the immense emptiness between galaxies. As astronomers continued their dedicated study of IC 1101, they slowly began to understand precisely why it was so incredibly massive. This galaxy did not achieve its enormous size through normal processes alone. It became such a colossal giant through an act of cosmic violence, a process that has been unfolding for billions of years. IC 1101 is what scientists rather dramatically call a cannibal galaxy. It has been actively eating other galaxies. To truly grasp galactic cannibalism, you need to think about how gravity operates on the very largest scales. Galaxies don't exist in complete isolation. They are grouped together in clusters, all held tightly together by their mutual gravitational attraction. Within these clusters, galaxies move around each other, sometimes passing incredibly close by, sometimes colliding directly. When two galaxies get close enough to each other, their immense gravity begins to distort their shapes. Stars get pulled out of their normal, predictable orbits. Gas and dust clouds get compressed and stretched into strange new forms. If the galaxies are somewhat similar in size, they might merge together over hundreds of millions of years, eventually forming a single, larger, combined galaxy. But if one galaxy is significantly bigger than the other, something quite different occurs. The larger galaxy simply absorbs the smaller one, stripping away its stars and gas, adding all of that material to its own massive body. This is precisely what has been happening to IC 1101 for billions of years. As the largest and most massive galaxy in its cluster, IC 1101 sits at the gravitational center of everything around it. Smaller galaxies that venture too close get irrevocably trapped by its enormous gravitational pull. They spiral inward, getting slowly torn apart and consumed over millions of years. Each meal makes IC 1101 a little bit bigger, a little bit more massive, a little bit more dominant in its cosmic neighborhood. Scientists estimate that IC 1101 has undergone at least 76 major mergers over its incredibly long history. 76 times, another substantial galaxy fell into this cosmic giant and was absorbed into its immense body. And those are just these major mergers. Countless smaller dwarf galaxies have also been consumed, galaxies so tiny that they barely registered as a significant meal for this enormous predator. The undeniable evidence for this cannibalistic history is clearly written in IC 1101's very structure. When you observe a galaxy like our Milky Way, you see a beautiful, distinct spiral pattern. Those spiral arms are active regions where stars are constantly forming, where vast clouds of gas are collapsing under gravity to create new stellar nurseries. Spiral galaxies typically possess abundant gas and dust, the essential raw materials needed for ongoing star formation, and they exhibit a distinct, rotating disk shape. IC 1101, however, looks nothing like this. It is what astronomers classify as an elliptical galaxy, meaning it has a smooth, oval, shaped appearance with no visible spiral arms at all. Elliptical galaxies often form when spiral galaxies violently merge together. The intense gravitational interactions during such a merger utterly destroy the delicate spiral structure, mixing all the stars together into a more random, spherical or oval distribution. The fact that IC 1101 is an elliptical galaxy tells us that it has experienced so many mergers that any original spiral structure it might have possessed has been completely erased. All of those collisions, all of that gravitational chaos, has stirred up the stars like someone mixing ingredients in a cosmic bowl. What remains is this smooth, relatively featureless giant, a silent testament to billions of years of relentless galactic consumption. But there is something even more remarkable about IC 1101. Despite containing 100 trillion stars, it is actually, in a sense, a dying galaxy. The stars within it are almost all extremely old. Most of them are what astronomers refer to as red giants or yellow stars, ancient stellar objects that have already burned through most of their nuclear fuel. Very few new stars are currently being born inside IC 1101. This might seem counterintuitive at first. With so many stars and such immense mass, you might expect IC 1101 to be a vibrant hotbed of stellar activity. But remember how it grew so large. Every time it consumed another galaxy, it also consumed that galaxy's gas supply. Gas is the crucial fuel for star formation. Without gas, new stars simply cannot be born. Over billions of years of this relentless cannibalism, IC 1101 has either used up or expelled most of its available gas. The mergers themselves were often violent enough to heat the gas to extreme temperatures, causing it to expand and escape the galaxy entirely, or to compress it so quickly that it all formed into stars at once in brief, intense bursts of activity. Either way, the end result is a galaxy that has effectively run out of raw material. What remains is a quiet giant, slowly fading into the cosmic night. The stars that exist now will continue to shine for billions of years to come. But as they eventually burn out and die, there will be no new generations to replace them. IC 1101 is like an ancient kingdom that has conquered all of its neighbors, but now has no children to carry on its legacy. It is massive, powerful, and utterly magnificent, but it is also slowly approaching the end of its active life. At the very heart of IC 1101 lies something even more incredible than the galaxy itself. Sitting right in the center of this cosmic giant is one of the largest known supermassive black holes in the entire universe. Every large galaxy, without exception, has a supermassive black hole at its core. Our own Milky Way, for instance, hosts one called Sagittarius A, which contains about 4 million times the mass of our Sun. The black hole at the center of the Andromeda Galaxy is even bigger, containing somewhere around 100 million to 200 million solar masses. But the black hole at the very core of IC 1101 is in a completely different league. Scientists estimate that it contains somewhere between 40 billion and 100 billion times the mass of our Sun. To put that into perspective, this single black hole might possess 20, 5,000 times more mass than the black hole at the center of our entire Milky Way galaxy. Let me try to help you truly comprehend just how unbelievably massive this is. If you could somehow weigh the Earth, you'd find it has a mass of about 6 trillion kilograms. That sounds like an enormous amount until you compare it to the Sun, which is about 330,000 times more massive than Earth. Our Sun is a fairly ordinary star by stellar standards, neither particularly large nor particularly small. Now, try to imagine multiplying the Sun's mass by 50 billion. That's roughly how much mass is incredibly packed into the supermassive black hole at IC 1101 center. All of that immense mass is compressed into a region of space from which absolutely nothing, not even light itself, can escape. The gravitational pull at the event horizon, which is the boundary of the black hole, is so intense that even light cannot break free and travel outward. The size of a black hole's event horizon depends directly on its mass. For a black hole with a mass of 50 billion solar masses, the event horizon would have a radius of roughly 150 billion kilometers. That might sound enormous, and it absolutely is. But remember that this is a region containing 50 billion times the mass of our Sun, all compressed into what is essentially a point at its center. The event horizon is simply the boundary beyond which escape becomes utterly impossible. To put this in even more perspective, our entire solar system, from the Sun all the way out to the orbit of Neptune, is about 9 billion kilometers across. The event horizon of IC 1101's central black hole is roughly 16 times larger than our entire solar system. If you could magically place this black hole where our Sun currently sits, its event horizon would extend well beyond the orbit of Pluto, engulfing everything we consider our cosmic home. What would it actually be like near this monstrous black hole? The physics governing such extreme environments is bizarre and incredibly counterintuitive. Time itself would pass differently near the event horizon compared to far away. Someone falling toward the black hole would see the outside universe speeding up incredibly, while an outside observer would see the falling person slow down and appear to freeze as they approached the horizon. From the outside, they would never seem to actually cross the boundary. Inside the event horizon, all directions universally lead toward the singularity at the very center. Space and time themselves become so warped and distorted that the very concept of escaping becomes utterly meaningless. The singularity, a point of theoretically infinite density, would tear apart anything that fell in, stretching it into long, thin strands through a horrifying process physicists have nicknamed spaghettification. But here's something truly remarkable. Despite its enormous size and terrifying properties, the black hole at IC 1101 center is currently relatively quiet. It's not actively devouring huge amounts of matter at the moment. There's no brilliant, swirling accretion disk of superheated gas around it. There are no powerful jets of material shooting into space at nearly the speed of light. The black hole is certainly there, patiently waiting, but it has already consumed most of the material that was easily within its gravitational reach. This current quietness is actually directly related to the same phenomenon that has stopped IC 1101 from forming new stars. Most of the gas in the galaxy has already been used up, and without gas falling toward the center, the black hole simply has very little to eat. Occasionally, a rogue star might wander too close and get torn apart, providing a brief, dramatic meal. But these events are quite rare. The black hole, much like the galaxy that hosts it, is a giant in repose, immensely powerful, but currently dormant. There are still subtle traces of the black hole's past activity. However, astronomers have detected a radio source at IC 1101 center, cataloged as PKSO 8.59. This radio emission originates from relativistic jets, which are streams of particles accelerated to nearly the speed of light and violently ejected from the vicinity of the black hole. These jets are powered by the black hole's rotation and its incredibly strong magnetic fields, and they can carve out enormous cavities in the surrounding hot gas. Images captured by X-ray telescopes clearly show these cavities. They appear as vast bubbles of very hot, very thin gas, blown outward by the immense energy released near the black hole. Some of these bubbles stretch millions of light years across, serving as powerful testimony to periods in the past when the black hole was much more active and energetic than it is today. The sheer energy required to inflate these bubbles is staggering, equivalent to the total energy output of billions of stars over millions of years. This kind of intricate feedback loop between supermassive black holes and their host galaxies is one of the most active and fascinating areas of research in modern astrophysics. Scientists now strongly believe that supermassive black holes play a crucial role in regulating both galaxy growth and their subsequent evolution. When gas flows toward a galaxy's center, the black hole can release enough energy to heat that gas and powerfully push it outward, effectively preventing it from collapsing and forming new stars. This creates a kind of thermostat effect that helps determine the final size and overall properties of galaxies. In IC 1101's case, this feedback mechanism may be partly responsible for the galaxy's current state. The black hole has helped shut down star formation by heating the gas and preventing it from cooling and collapsing. The giant galaxy and its giant black hole have reached a kind of equilibrium, each one having shaped the other over billions of years of shared, complex evolution. Black holes inherently grow by consuming matter that falls into them. When galaxies merge, the supermassive black holes at their centers eventually find each other and merge as well. Over the course of IC 1101's long and violent history of galactic cannibalism, its central black hole has been fed again and again. Every galaxy that IC 1101 consumed added to the mass of this growing monster. Every merger brought in more fuel for the black hole's insatiable appetite. The process by which two supermassive black holes merge is both fascinating and incredibly violent. When two galaxies collide, their central black holes don't immediately find each other. They are initially separated by vast distances and surrounded by billions of stars. But as the merger progresses, gravitational friction with the surrounding stars causes the black holes to slowly spiral toward the center of the newly combined galaxy. Eventually, the two black holes get close enough to form a binary system, orbiting tightly around each other. As they orbit, they continuously lose energy through the emission of gravitational waves, which are ripples in the very fabric of space-time itself. These gravitational waves carry energy away from the binary system, causing the orbit to steadily shrink. The black holes spiral closer and closer, orbiting faster and faster, until finally they merge in a catastrophic event that releases truly enormous amounts of energy. When two supermassive black holes merge, the gravitational waves they produce are among the most powerful events in the entire universe. The final merger releases more energy than all the stars in a typical galaxy combined, though most of this energy is in the form of gravitational waves rather than visible light. These waves ripple outward at the speed of light, stretching and squeezing space itself as they pass. We have only recently developed the technology to directly detect these gravitational waves. The first direct detection occurred in 2015 when the LIGO observatories measured waves from two stellar, mass black holes merging about 1 billion light-years away. Since then, dozens of gravitational wave events have been observed, opening up an entirely new way of studying the universe. Future gravitational wave detectors, like the planned LISA mission that will fly in space, will be able to detect mergers of supermassive black holes. When LISA launches, perhaps in the 2030s, It might actually detect events similar to the mergers that built up IC 1101's central black hole. We will literally be able to listen to the universe as giant black holes collide and merge, adding another sense to our astronomical toolkit. IC 1101's black hole has experienced dozens of such mergers over its long history. Each merger added mass and altered the black hole's spin. The process of multiple mergers also significantly affected the surrounding galaxy, as the merging black holes flung stars outward through intense gravitational interactions. This is probably why IC 1101's core is so large yet relatively faint. Repeated black hole mergers have scattered stars away from the very center, creating a core profile that is quite unusual for galaxies of this immense size. The event horizon of a black hole, which is the ultimate boundary beyond which nothing can escape, gets larger as the black hole gains more mass. For a black hole containing 50 billion solar masses, the event horizon would extend outward for about 150 billion kilometers. That's roughly the distance from our Sun to the outer reaches of our solar system, all contained within a region of space where not even light can escape. Around this supermassive black hole, there is a bright radio source that astronomers have cataloged as PKSO 859. This radio emission originates from jets of material being blasted outward from the vicinity of the black hole at nearly the speed of light. Even though the black hole is not as active as it once was, it still occasionally flares to life, releasing enormous amounts of energy into the surrounding space. The presence of such an enormous black hole raises fascinating questions about the fundamental connection between galaxies and the monstrous objects at their hearts. Scientists have discovered that there's a strong relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. Bigger galaxies tend to have bigger black holes. But a fundamental question arises: which came first? Did the black holes form initially and then gradually grow their galaxies around them? Or did the galaxies form first and then slowly build up their black holes over vast spans of cosmic time? The answer, it seems, is that they grew together, each one profoundly influencing the development of the other. As IC 1101 consumed more and more galaxies, its central black hole also consumed the black holes from those galaxies. The two processes fed into each other, creating a powerful feedback loop that ultimately produced both the largest known elliptical galaxy and one of the largest known black holes in existence. The very core of IC 1101 is also remarkable for its sheer size. A study conducted in 2017 utilizing images from the formidable Hubble Space Telescope measured the galactic core and found that it stretches across nearly 14,000 light-years. That means just the central core of IC 1101, not the entire galaxy, but merely its innermost region, is actually bigger than most entire dwarf galaxies. This core alone contains more stars than most complete galaxies in the universe. Now, I want to take you on a brief mental journey to help you truly appreciate the scale of what we are discussing. Imagine you could somehow travel from one end of IC 1101 to the other. You would need to traverse somewhere between 4 and 6 million light-years. Remember, light travels at an astounding speed of about 6 trillion miles per year. Even at that incomprehensible velocity, crossing IC 1101 would demand millions of years. But let's try another comparison. The Voyager 1 spacecraft, famously launched by NASA in 1977, is the fastest human-made object ever to leave our solar system. It's currently traveling at about 38,000 miles per hour relative to the Sun. At that speed, Voyager 1 would take approximately 80,000 years just to reach the nearest star to our Sun, Proxima Centauri, which is only about 4 light-years away. To cross the entire Milky Way at Voyager 1's speed, it would take roughly 2 billion years. And to cross IC 1101, you would need somewhere between 80 billion and 120 billion years. That is, quite frankly, more time than the universe has even existed. Even with our fastest spacecraft, crossing this single galaxy would be a completely impossible feat. Here's another way to conceptualize it. If you could shrink our entire Milky Way down to the size of a dinner plate, roughly 10 inches across, then IC 1101 would be the size of a very large swimming pool. Our entire galaxy, with all of its hundreds of billions of stars, with the beautiful spiral arms where we make our home, would be just a tiny dish floating in a vast, immense sea. Or consider this: light from IC 1101 has traveled for over 1 billion years to finally reach us. In all that unimaginable time, light has been continuously streaming away from this galaxy in every conceivable direction. Every single second, IC 1101 radiates enough light to travel about 186,000 miles. Over 1 billion years, that light has traversed 1 billion light years, which is approximately 6 billion trillion miles, and it is only now just arriving at our telescopes. Ancient photons that left their home galaxy when Earth was still in its very early stages of complex life. The discovery and subsequent study of IC 1101 would simply not have been possible without tremendous advancements in telescope technology. In the early days of astronomy, telescopes were severely limited by the physical size of their lenses and mirrors. Larger telescopes could certainly gather more light and thus see fainter objects. But there were practical limits to how big you could realistically make a telescope on the ground. The Earth's atmosphere also posed a significant problem. Our planet's atmosphere is constantly moving and shimmering, which is precisely why stars appear to twinkle. This twinkling effect blurs the images that ground-based telescopes can capture, severely limiting how clearly they can resolve distant objects. For most of the 20th century, astronomers could discern that IC 1101 existed and was indeed very large, but they simply couldn't study its detailed structure with any clarity. Everything changed dramatically with the successful launch of the Hubble Space Telescope in 1990. Floating high above the distorting effects of the atmosphere, Hubble could capture images with absolutely incredible clarity. Over the decades since its launch, Hubble has observed IC 1101 multiple times, meticulously revealing intricate details about its core, its sprawling surrounding halo of stars, and its complex relationship to the other galaxies within its cluster. More recently, astronomers have employed a variety of other powerful telescopes to study IC 1101 at different wavelengths of light. Radio telescopes have successfully detected the unique emission emanating from its central black hole. X-ray telescopes have observed the incredibly hot gas that fills the cluster around it. Infrared telescopes have peered through the obscuring dust to meticulously study the stellar populations within the galaxy. Each new observation, across these different wavelengths, adds another crucial piece to our ever-growing understanding of this cosmic giant. But there is still much we don't fully comprehend. The exact number of stars in IC 1101 remains uncertain because counting stars in such a distant galaxy is incredibly difficult, a monumental task. The precise size of the galaxy also depends on how you choose to define where it truly ends, since galaxies don't possess sharp, definitive boundaries but rather gradually fade into the darkness of intergalactic space. The mass of the central black hole is known only approximately, because measuring black hole masses at such immense distances involves many complex assumptions and models. What we do know is that IC 1101 represents something close to an upper limit for how large galaxies can actually get. There may be slightly larger galaxies out there, patiently waiting to be discovered. In fact, in 2022, astronomers announced the groundbreaking discovery of a galaxy called Alcyonius, which boasts radio lobes extending across an astonishing 16 million light-years. However, Alcyonius is a special case. Its truly enormous size stems from giant jets of material power fully shooting out from its central black hole, not from its actual stars and normal galactic material. When it comes to the true body of a galaxy, the colossal collection of stars, gas, and dark matter that makes up its fundamental substance, IC 1101 remains one of the largest ever found. It sits at the extreme end of the galactic size distribution, a genuine monster among giants. The story of IC 1101 also imparts something profound about the very nature of the universe and the passage of cosmic time. Galaxies don't form all at once as a single event. They grow slowly, patiently, over billions of years through a continuous process of accumulation and merger. Small galaxies form first from collapsing clouds of primordial gas. Those small galaxies then merge together to form larger ones. Larger galaxies merge to form even larger ones. And on it goes, with the biggest galaxies growing ever larger by steadily consuming their smaller neighbors. This grand process is known as hierarchical structure formation, and it's one of the fundamental principles of modern cosmology. The universe builds things from the bottom up, starting small and growing large through countless mergers over immense cosmic time. IC 1101 is simply the most extreme example of this process that we have uncovered so far. It has had billions of years and a perfect location at the very center of a rich galaxy cluster to grow to its incredible, unparalleled size. But this growth cannot, and will not, continue forever. IC 1101 has already consumed most of the galaxies that were close enough to fall into its gravitational grasp. Those that remain are either too far away or moving too fast to be effectively captured. The surrounding cluster is slowly spreading out due to the relentless expansion of the universe, carrying potential victims farther and farther from IC 1101's gravitational reach. At the same time, the larger universe is changing in ways that will eventually affect every single galaxy, including this enormous one. Space itself is expanding, and not just expanding, but actually accelerating in its expansion. This acceleration is driven by something scientists refer to as dark energy, a mysterious force that constitutes about 68% of the total energy in the universe, but whose true nature we currently don't understand at all. Let me explain dark energy a bit more, because it's one of the most fascinating and puzzling discoveries in all of science. For most of the 20th century, astronomers generally assumed that the expansion of the universe was gradually slowing down. This made intuitive sense. Everything in the universe is exerting a gravitational pull on everything else through gravity. You would naturally expect all that gravitational attraction to act like a cosmic brake, gradually slowing the expansion that began with the Big Bang. In 1998, however, two independent teams of astronomers made a truly shocking discovery. They were meticulously measuring the expansion rate of the universe by observing distant supernovas, using them as standard candles to precisely calculate cosmic distances. What they found was completely unexpected. The universe was not slowing down its expansion. It was actually speeding up. Distant galaxies were moving away from us faster than closer ones, and the rate of expansion was accelerating over time. This discovery was so unexpected that the astronomers initially thought they had surely made a mistake or an error in their measurements. But as more data poured in from more supernovas and from other independent observations, the result consistently held up. Something was actively pushing the universe apart, counteracting gravity, and causing space itself to expand at an ever-increasing rate. Scientists named this mysterious force dark energy, though the name, unfortunately, tells us very little about what it actually is. We know that dark energy makes up about 68% of all the energy in the universe. We know that it acts as a kind of anti-gravity, pushing space apart rather than pulling it together. We know that its effects become more pronounced and important over time as the universe expands and ordinary matter becomes more spread out. But we still don't know what dark energy is truly made of, where it comes from, or why it possesses the strength that it does. It might be an inherent property of empty space itself, something called the cosmological constant that Albert Einstein once proposed, and then famously called his biggest blunder. It might be a new, undiscovered kind of energy field that pervades the entire universe. It might even be a sign that our current understanding of gravity is incomplete and needs to be fundamentally revised. What we do know is that dark energy is actively reshaping the future of the cosmos. As space expands faster and faster, distant objects recede from us at ever-increasing speeds. There's a definite limit to how fast light can travel, but there is no known limit to how far space itself can expand. Eventually, objects will be carried away from us by the expansion of space faster than their light can ever travel toward us. When that happens, they will vanish completely behind a cosmic horizon, forever beyond our reach. For IC 1101, this means that its days of growth through galactic cannibalism are definitively numbered. Eventually, there will simply be no more galaxies left for it to consume. It will become isolated, a lonely giant floating in an ever-emptying universe, quietly watching as one by one, the other galaxies fade from view. Let me paint a more detailed picture of what this incredibly distant future looks like. Remember that IC 1101 sits comfortably within the Abell 2029 galaxy cluster, surrounded by hundreds of other galaxies. These galaxies are all bound together by gravity, patiently orbiting around their shared center of mass. For now, gravity is strong enough to keep the cluster cohesive, resisting the relentless expansion of space. But in approximately 100 billion years, the universe's expansion will have accelerated to the point where galaxies outside the local supercluster will start to disappear beyond the cosmic horizon. From IC 1101's perspective, the night sky will slowly begin to empty. One by one, distant galaxy clusters will fade from view, their light no longer capable of reaching across the ever-expanding void. The observable universe, which currently contains about 2 trillion galaxies, will steadily shrink and shrink. Within the Abell 2029 cluster itself, things will be different for a while longer. The galaxies there are close enough and bound tightly enough that they will remain together, even as the larger universe empties out. Over the next several billion years, these galaxies will continue to interact, merge, and evolve. IC 1101 might still consume a few more victims, growing slightly larger even as the rest of the universe slips away. But eventually, even the galaxies within the cluster will merge together. The same immense processes that built IC 1101 will continue, drawing the remaining galaxies toward the center, where they will be absorbed into an even larger, combined structure. In the very long run, perhaps in several hundred billion years, all the galaxies in the Abell 2029 cluster might merge into a single, enormous galaxy, even more massive than IC 1101 is today. By that incredibly distant time, however, the universe beyond the cluster will be essentially empty. No light from distant objects will be reaching the cluster anymore. The night sky, if any observers still existed, would reveal only the stars of the local, merged galaxy against a backdrop of absolute, impenetrable blackness. The rest of the cosmos would have slipped beyond the horizon, completely unreachable and utterly unknowable. This is the profound isolation that awaits IC 1101 and, indeed, every other gravitationally bound structure in the universe. Each island of matter will be left alone with itself, cut off from everything else by the relentless, accelerating expansion of space as the eons roll by. But even this isn't the final fate of IC 1101. What ultimately happens to a galaxy in a universe that is slowly winding down toward heat death? The answer is as magnificent as it is melancholic. Over the next 100 trillion years, the stars within IC 1101 will slowly, inexorably burn out. The most massive blue stars would have vanished long ago, exploding as brilliant supernovas or collapsing into dense black holes. The middle-sized stars, much like our own Sun, will eventually puff up into red giants, shed their outer layers as beautiful glowing nebulas, and then quietly fade away as white dwarfs. Even the smallest, longest-lived stars, the red dwarfs that burn their nuclear fuel so incredibly slowly they can shine for trillions of years, will eventually exhaust their hydrogen and go dark. Let me walk you through this stellar death in a bit more detail, because the timescales involved are truly mind-boggling. The most massive stars in IC 1101, the blue giants and super giants, lived fast and died young. They burned through their fuel in just a few million years before dramatically exploding as supernovas. Any blue giants that IC 1101 once possessed would have burned out billions of years ago. The galaxy today is overwhelmingly dominated by older, smaller, much longer-lived stars. Stars most similar to our Sun have average lifetimes of about 10 billion years. Our Sun is roughly halfway through its life, with about 5 billion years left before it swells into a red giant and eventually becomes a white dwarf. In IC 1101, many Sun-like stars have already completed this entire process, leaving behind white dwarf remnants. Others are still shining, but over the next several billion years, they too will burn out. But the most numerous stars in any galaxy are the red dwarfs. These are tiny stars with only a fraction of the Sun's mass. Red dwarfs burn their fuel so incredibly slowly that they can continue to shine for trillions of years. A red dwarf born at the same time as our Sun will still be shining long after the Sun has become a cold white dwarf. In IC 1101, with its 100 trillion stars, there are untold numbers of red dwarfs. These tiny, dim stars will be the very last to go out. For trillions of years after the larger stars have died, the red dwarfs will continue to burn, providing the only light in an otherwise darkening galaxy. But even red dwarfs have their limits. The smallest red dwarfs, with perhaps 8% of the Sun's mass, can burn for up to 10 trillion years. That's about 700 times the current age of the universe. But eventually, even they will exhaust their hydrogen fuel and fade into darkness. Scientists estimate that star formation in the universe will effectively cease in about 100 trillion years. By that unimaginably distant time, the gas and dust needed to make new stars will have been used up or dispersed too thinly to collapse under gravity. No new stars will be born to replace the ones that have died. The glorious era of starlight will be completely over. One by one, the 100 trillion stars of IC 1101 will wink out. The galaxy will grow dimmer and dimmer over timescales that make the current age of the universe seem like the blink of an eye. Where once there was a blaze of stellar light, there will eventually be nothing but the cold, dark remnants of dead stars, white dwarfs, neutron stars, and black holes, all drifting through an ever-expanding void. The universe at this stage will be an incredibly dark place, but not an empty one. All those stellar remnants, all those white dwarfs and neutron stars and black holes will still exist. They will orbit through the merged remnant of what was once IC 1101 and its cluster companions. The galaxy will be a ghost of its former self, populated by the silent corpses of stars rather than by living, burning suns. But even this is not the absolute end. Over even longer timescales, measured in years with so many zeros that writing them out would fill pages, even these stellar corpses will slowly decay. White dwarfs will gradually cool until they become black dwarfs, hypothetical objects that no longer emit any light at all. This cooling process takes an almost inconceivable amount of time. A white dwarf cools to near absolute zero only after about 10 to the 15th power years, or roughly a million billion years. That's about 100,000 times longer than the current age of the universe. Neutron stars might also decay as their fundamental particles gradually break down. We aren't entirely sure about this, because it depends on whether protons, the essential building blocks of atomic nuclei, are truly stable or whether they eventually decay. Some theories of particle physics predict that protons should decay with a half-life of around 10 to the 34th power years or even longer. If this proves true, then over unfathomably long time spans, even the matter that makes up neutron stars and white dwarfs and planets and everything else will gradually dissolve into pure radiation. And the black holes, including that enormous monster at the center of IC 1101, will slowly evaporate through a process called Hawking radiation. Stephen Hawking famously discovered that black holes aren't truly black. They slowly leak particles and radiation over immense time spans, gradually shrinking as they do so. This phenomenon occurs because of quantum mechanical effects near the event horizon. In the strange world of quantum physics, particle pairs are constantly popping into existence and then annihilating each other. Near a black hole's event horizon, one member of such a pair can fall into the black hole while the other successfully escapes into space. Over time, this process drains energy from the black hole, causing it to slowly shrink. The rate of Hawking radiation is incredibly slow for large black holes. A black hole with the mass of our Sun would take about 10 to the 67th power years to completely evaporate. That's a 1 followed by 7 zeros. But the supermassive black hole at the center of IC 1101 is billions of times more massive than the Sun, and the time required for it to evaporate is correspondingly far, far longer. A black hole containing 50 billion solar masses would take something like 10 to the 100th power years to evaporate, or maybe even longer. That's a Google years, a 1 followed by 100 zeros. To write out that number in full would require more paper than exists on Earth. It is a span of time so unimaginably vast that everything we have discussed so far, from the Big Bang to the eventual death of the last stars, is not even a rounding error by comparison. But even this immense period of time is not infinite. Eventually, trillions upon trillions upon trillions of years from now, even the supermassive black hole at the heart of IC 1101 will have radiated away its last bit of energy and completely disappeared from the universe in a final, quiet burst of Hawking radiation. When that finally happens, there will be absolutely nothing left of IC 1101 at all. No stars, no black holes, no remnants of any kind, just the particles and radiation that once made up a magnificent galaxy, spreading out through an ever-expanding, ever-cooling, ever-darkening universe. The largest galaxy we have ever found will have followed the same ultimate path as every other structure in the cosmos, dissolving into the endless night. This vision of the far future might seem incredibly bleak, but I personally find something strangely beautiful about it. IC 1101 exists right now, in this brief, fleeting moment of cosmic history, when stars still shine and galaxies still glow. It has existed for billions of years, and it will continue to exist for billions more. In the grand sweep of cosmic time, the era of stars and galaxies is just a passing phase, a brief, vibrant flowering of complexity between the chaos of the early universe and the cold, empty silence of the far future. We are incredibly lucky enough to exist during this flowering. We are lucky enough to have evolved intelligence, built powerful telescopes, and pointed them at the mysterious sky. We are lucky enough to have discovered IC 1101 and to understand, at least in part, what it is and how it came to be. In all the vast history of the universe, stretching from the Big Bang to the final heat death, this moment right now is truly special. It is the moment when the universe has developed the profound ability to look at itself and wonder. And what we observe when we look at IC 1101 is the grandest scale on which the universe has assembled matter into organized structures. We see billions of years of cosmic history written clearly in its stars. We see the results of countless galactic mergers, countless collisions, countless acts of gravitational violence that have somehow, miraculously, produced something utterly magnificent. We see a monster, yes, but also a monument. A monument to the immense forces that shape our universe and to the intricate processes that have been building complexity ever since the very first atoms formed. Let me bring us back closer to home for a moment. Our own Milky Way is not immune to the powerful forces that shaped IC 1101. We, too, are actively participating in the cosmic dance of galactic interaction and merger. Right now, as you listen to these words, our galaxy is in the ongoing process of consuming several smaller galaxies. The Canis Major Dwarf Galaxy, for instance, is being slowly ripped apart and absorbed into the Milky Way's vast structure. The Sagittarius Dwarf Galaxy is being stretched and distorted by our powerful gravitational pull. Streams of stars from past victims can be subtly traced across our night sky, ghostly reminders of galaxies that once existed as separate, distinct entities. And in the future, an even more dramatic event awaits us. The Andromeda Galaxy, our nearest large neighbor, is undeniably heading directly toward us. Scientists have long believed that in about 4 to 5 billion years, the Milky Way and Andromeda would collide and eventually merge into a single, larger galaxy, often playfully nicknamed Milkomeda. Recent research, however, has introduced some fascinating uncertainty into this prediction. New studies, using advanced data from the Gaia spacecraft and the Hubble Space Telescope, suggest that the collision might not be as certain as we once thought. When scientists account for the gravitational influence of other nearby galaxies, such as the Large Magellanic Cloud and the Triangulum Galaxy, the probability of a direct head-on collision drops significantly. Some simulations now suggest only about a 50% chance of a merger happening within the next 10 billion years. But whether it occurs in 4 billion years, or 10 billion years, or perhaps not at all, the process itself clearly illustrates the same fundamental forces that created IC 1101. Galaxies interact, merge, and consume each other. It is simply the way of the universe. Even our own quiet corner of the cosmos actively participates in this grand cosmic competition. If the merger does happen, the results would be spectacular, at least on cosmic timescales. The collision itself wouldn't be violent in the way you might imagine. Stars are so incredibly far apart that the chances of any two individual stars actually hitting each other are essentially zero. But the gravitational effects would be absolutely dramatic. The delicate spiral structures of both galaxies would be destroyed, completely reshaped. Gas clouds would be compressed, triggering enormous bursts of star formation, igniting new stellar nurseries across the merged entity. The two supermassive black holes at the centers of each galaxy would eventually find each other and merge, releasing powerful gravitational waves that would ripple across the universe. Over billions of years, the initial chaos would slowly settle down. What was once the Milky Way and what was once Andromeda would blend together into a single, large elliptical galaxy, much like IC 1101, but on a smaller scale. Future astronomers, if any exist at that time, might look back at ancient records and marvel that their smooth, featureless home galaxy was once two beautiful spirals, gracefully dancing through the void. By that time, of course, Earth will be long gone. Our sun is expected to expand into a red giant in about 5 billion years, swelling to a size that would completely engulf our planet. Whether humanity survives until then, whether we manage to spread to other star systems, whether intelligence of any kind persists in the universe, these are profound questions we cannot yet answer, but the story of IC 1101 powerfully reminds us that the universe operates on timescales that utterly dwarf individual lives, individual civilizations, and even individual planets. I want to return now to the question of what IC 1101 tells us about our place in the universe. When you gaze up at the night sky, you might feel incredibly small. You might feel insignificant in the face of such immense vastness. But I believe the existence of IC 1101 actually tells us something profoundly hopeful about our situation. First, consider that we can even know about IC 1101 at all. A galaxy more than 1 billion light-years away, containing 100 trillion stars, and we have figured out how big it is, how it formed, and what lies at its very center. That is truly remarkable. Human beings, living on a small, rocky planet orbiting an ordinary star in an unremarkable part of an average spiral galaxy, have somehow developed the profound ability to understand objects so incredibly far away that their light left before complex life even existed on Earth. This ability to understand is not insignificant. In a universe of mindless matter and energy, of particles simply bouncing around according to physical laws, somehow here on Earth, consciousness has emerged. Minds that can wonder, question, investigate, and learn. Whatever else we are the part of the universe that has woken up and started actively asking questions about itself. Second, consider that IC 1101, for all its enormity, is made of the very same stuff we are. The stars in IC 1101 are fusion reactors, just like our Sun. They burn hydrogen into helium and heavier elements, just like stars do everywhere. The atoms in those distant stars are the same kinds of atoms that make up our body's carbon, oxygen, nitrogen, iron. All of them were forged in the hearts of stars somewhere in the universe. Just as the atoms in our bodies were forged in stars that exploded before our Sun was born, there is a deep continuity here, a fundamental connection between us and everything else in the cosmos. We are not separate from the universe. We are an integral part of it. The same processes that built IC 1101 built us. The same atoms that shine in distant galaxies shine in our eyes. We are not external observers of the universe. We are the universe observing itself from within. Third, consider what it means that galaxies like IC 1101 can exist at all. The universe didn't have to be this way. If the fundamental constants of physics were even slightly different, if gravity were a little stronger or the nuclear forces a little weaker, stars and galaxies might never have formed. The universe might have collapsed back on itself moments after the Big Bang, or expanded so fast that matter never clumped together into anything interesting. Instead, we live in a universe where physical laws allow for the formation of stars, planets, galaxies, life, and ultimately mind. IC 1101 is a powerful testament to what is possible in such a universe. It is proof that matter and energy, simply following physical rules over billions of years, can organize itself into structures of staggering complexity and profound beauty. If the universe can produce IC 1101, what else might it be capable of? What other wonders exist out there that we have not yet discovered? This brings me to the final point I want to make about IC 1101 and about our ongoing quest to understand the universe. Every discovery we make, every galaxy we study, every black hole we observe expands our sense of what is possible. A few centuries ago, people genuinely thought Earth was the absolute center of everything. Then, we learned that we orbit the Sun. Then we learned that the Sun is just one star among hundreds of billions in our galaxy. Then we learned that our galaxy is one of trillions. Each step in this journey has made us smaller in some sense. But it has also made the universe grander, more interesting, and more worthy of our awe. IC 1101 is another significant step in that incredible journey. It shows us that the universe can build things far larger than we ever imagined. It challenges us to keep asking questions, to keep looking further, to keep pushing the boundaries of what we know. And it powerfully reminds us that for all our insignificance on cosmic scales, we are the ones doing the asking, doing the looking, and doing the pushing. In the face of IC 1101's sheer enormity, we can choose to feel small or we can choose to feel wonder. I choose wonder. As we wrap up this exploration of the biggest galaxy ever discovered, I want to leave you with one final, profound image. Imagine yourself gently floating in the vastness of space, somewhere near the very edge of IC 1101. Around you, in every single direction, stars stretch out toward what seems like infinity. Not just hundreds, not thousands, not even millions, but literally trillions of stars. Each one of those distant points of light is a sun. Each one might host planets of its own. Each one has been shining for billions of years, a silent beacon in the cosmic night. You cannot see the center of the galaxy from this vantage point. It's simply too far away, hidden behind countless curtains of intervening stars, an impenetrable veil of stellar light. You also cannot clearly discern the edge. The galaxy gradually fades into the darkness of intergalactic space, with no sharp or obvious boundary. You are utterly lost in a boundless sea of light, adrift within a structure so unfathomably vast that crossing it would take millions of times longer than human civilization has even existed. And yet, from a small, rocky planet more than 1 billion light-years away, tiny beings who live for less than a cosmic instant have somehow managed to figure out that this incredible place exists. They have measured its immense size, they've counted its countless stars, and they've even located the monstrous black hole at its very heart. They have meticulously traced its turbulent history back billions of years and projected its future trillions of years hence. They have placed it within the grand context of an entire universe and marveled at its sheer grandeur. That is perhaps the most astonishing thing of all, not merely that IC 1101 exists, but that we, fragile and fleeting as we are, know that it exists. But before we fully conclude, I want to dive even deeper into some of the most fascinating aspects of what we've discussed. Because truly understanding IC 1101 isn't just about memorizing colossal numbers and scientific facts. It's about comprehending the fundamental, underlying processes that have shaped everything in our universe, including us. Let's talk more about what truly happens inside a galactic merger. When I say that IC 1101 has consumed dozens of other galaxies, it might sound like a simple, straightforward process, like one object merely swallowing another. But the reality is far more complex, far more dynamic, and arguably far more beautiful than any simple description can capture. When two galaxies first begin to interact, the initial phase is a gravitational dance, slow and majestic on cosmic scales. Even when the galaxies are millions of light-years apart, they can feel each other's subtle gravitational pull. This distant gravity slowly begins to distort their shapes, ever so slightly. Stars that were orbiting peacefully within their own galaxy begin to feel a distinct tug from an unexpected direction. Vast gas clouds that were drifting calmly along start to move in strange, new ways. As the galaxies draw closer, these gravitational effects become significantly more pronounced. If you could somehow watch a galactic merger in fast forward, compressing millions of years into just a few minutes, you would witness the galaxies stretching and warping like taffy being pulled apart. Long, elegant streams of stars get drawn out from each galaxy, forming what astronomers dramatically call tidal tails. These tails can extend for hundreds of thousands of light-years into space, ghostly ribbons of stars that eloquently mark the immense violence of the interaction. The first close pass between two galaxies is often not the final collision. Instead, the galaxies swing past each other, their mutual gravity slowing them down considerably. They then separate again, moving apart for a time. But by now, they are gravitationally bound together. Like cosmic dancers who have clasped hands, they cannot escape each other's embrace. Over the next few 100 million years, they will swing back and forth, getting incrementally closer with each pass, until finally they merge completely into a single, unified entity. During this tumultuous process, something truly remarkable happens. The immense gas in both galaxies gets intensely compressed by powerful gravitational forces and shock waves. This compression acts as a trigger, igniting massive bursts of star formation. New stars light up by the billions, burning incredibly hot and bright. Astronomers call these spectacular events starbursts, and they can temporarily make a merging galaxy one of the brightest, most luminous objects in its entire part of the universe. In some mergers, so much gas gets violently driven toward the centers of the galaxies that it falls directly into the supermassive black holes patiently waiting there. This sudden, feeding frenzy causes the black holes to release tremendous amounts of energy, shining as incredibly luminous quasars that can be observed across billions of light years of space. The cores of the merging galaxies blaze with the fierce light of material being consumed by these hungry black holes, often outshining all the stars in both galaxies combined. Eventually, the initial chaos slowly settles down. The two galaxies become one. The new, combined galaxy is indeed larger than either of its predecessors, but it also looks fundamentally different. The beautiful spiral arms that might have graced the original galaxies are completely gone, utterly destroyed by the gravitational violence of the merger. What remains is typically an elliptical galaxy, smooth and relatively featureless, its stars orbiting in a complex tangle of different directions rather than in the orderly, flat disk of a spiral. This is precisely what happened to IC 1101, not just once, but dozens and dozens of times throughout its long history. Each merger added more stars, added more mass, and added more material to the central black hole. Each merger erased more of whatever original structure the galaxy might have had. Over billions of years of this relentless process, IC 1101 grew to become the incredible monster we observe today. Scientists can actually trace some of the subtle evidence of these past mergers. When astronomers meticulously study the stars within IC 1101, they discover distinct populations of stars with different ages and differing chemical compositions. These different populations are like geological layers in rock, each one recording a different era of the galaxy's long and violent history. Some stars are incredibly old, likely original members of the proto-galaxy that existed billions of years ago. Others are younger, formed during starburst events triggered by mergers. Still others possess unique chemical signatures that clearly show they originally formed in entirely different galaxies. Foreign stars now permanently absorbed into IC 1101's massive body. The very core of IC 1101 itself tells a compelling story of its violent history. As I mentioned earlier, the core is enormous, stretching nearly 14,000 light-years across. But it is also unusually faint for its immense size. Scientists believe this is because the repeated mergers and the intense activity of the central black hole have actually scattered stars away from the very center. Here's what they theorize happened. When two supermassive black holes merge, they first form a binary system, orbiting tightly around each other. As they spiral closer together, they gravitationally interact with stars passing nearby, flinging many of them outward with tremendous speed. This process, known as gravitational scarring, can effectively empty out the very center of a galaxy, creating a region with far fewer stars than you would normally expect. IC 1101 has experienced so many mergers that its core has been scarred repeatedly over cosmic time. The result is a massive core that is actually underpopulated with stars compared to what theoretical models would predict. Scientists estimate that hundreds of billions of solar masses worth of stars may have been scattered from the core over the course of IC 1101's history. That is an enormous amount of stellar material, more than the entire mass of many normal galaxies, flung outward into the halo, or even completely ejected from the galaxy itself. This kind of intricate detective work is what makes astronomy so profoundly fascinating. We cannot physically visit IC 1101. We cannot send probes there or collect samples directly. All we have is the light that patiently reaches our telescopes across unimaginable distances. But from that light, we can deduce an incredible amount about what has transpired over billions of years. We can literally read the history of the cosmos, written in the ancient language of photons. Let me now expand our perspective even further. IC 1101 is the largest galaxy of a certain type that we have found so far, but the universe is absolutely full of extreme objects. Understanding where IC 1101 fits within the cosmic zoo of galaxies helps us to truly appreciate just how remarkable and unique it is. At one end of the galactic size scale are dwarf galaxies. These are the smallest galaxies in the universe, containing anywhere from a few million to a few billion stars. Our own Milky Way has dozens of dwarf galaxies orbiting around it as satellites. The smallest of these, like Segu 1, contain only about 1,000 stars. They are so faint and diffuse that astronomers didn't even discover them until advanced surveys began in the 21st century. Dwarf galaxies play a crucial role in cosmic evolution. They are, in essence, the fundamental building blocks from which larger galaxies are gradually assembled. In the early universe, when the very first galaxies were forming, most of them were dwarfs. These small galaxies then merged with each other over billions of years, steadily building up the larger, more complex galaxies we observe today. Every large galaxy, including our Milky Way, and most certainly including IC 1101, started as humble dwarf galaxies that came together long, long ago. Moving up in size, we find galaxies like the Large Magellanic Cloud, which orbits our Milky Way at a distance of about 160,000 light-years. The Large Magellanic Cloud contains approximately 30 billion stars and has a diameter of about 14,000 light-years. It is clearly visible to the naked eye from the southern hemisphere as a faint, cloud-like patch in the night sky. The Large Magellanic Cloud is, in fact, being slowly absorbed by the Milky Way right now. Gas is being stripped from it, and eventually, it will merge completely with our galaxy, adding its stars to our growing collection. This is galactic cannibalism in action, happening right in our own cosmic backyard. Then we have galaxies similar in scale to our own Milky Way. Spiral galaxies of this size typically contain between 100 billion and 400 billion stars and have diameters ranging from 100,000 to 200,000 light-years. They are quite common in the local universe. Beautiful pinwheels of gas and stars, places where star formation continues even after billions of years of existence. Our nearest large neighbor, the Andromeda Galaxy, is somewhat larger than the Milky Way. It contains about 1 trillion stars, perhaps 2 or 3 times as many as our galaxy. Andromeda's disk stretches about 220,000 light-years across, making it roughly twice the diameter of the Milky Way. If you venture to a dark location on a clear autumn night in the northern A's, we wrap up this exploration of the biggest galaxy ever discovered. I want to leave you with one final image. Imagine yourself floating in the vastness of space, somewhere near the very edge of IC 1101. Around you, in every single direction, stars stretch out toward infinity. Not just hundreds, not thousands, not millions, but truly trillions of stars. Each one is a sun. Each one might have its own system of planets. Each one has been shining for billions of years. You couldn't see the center of the galaxy from here. It's simply too far away, hidden behind countless curtains of stars. You also couldn't see the exact edge either. The galaxy fades gradually into the darkness of intergalactic space, without any clear, sharp boundary. You would be utterly lost in a boundless sea of light, adrift within a structure so impossibly vast that crossing it would take millions of times, longer than human civilization has even existed. And yet, from a small, rocky planet more than 1 billion light-years away, beings who live for less than a cosmic instant, have somehow figured out that this place exists. They have measured its immense size, estimated its countless stars, and even located the supermassive black hole at its very heart. They have traced its history back billions of years and projected its future trillions of years hence. They have placed it in the context of an entire universe and marveled at its grandeur. That is perhaps the most amazing thing of all. Not merely that IC 1101 exists, but that we here know that it does. But before we fully conclude, I want to briefly revisit some of the most fascinating aspects of what we've discussed. Because understanding IC 1101 isn't just about memorizing staggering numbers and scientific facts. It's about understanding the fundamental processes that have shaped everything in our universe, including us. We delved into the incredible violence and beauty of galactic mergers, seeing how IC 1101 grew into a cannibal galaxy by absorbing its neighbors. We imagined the gravitational dance, the tidal tails stretching for hundreds of thousands of light years, and the eventual settling into a smooth, elliptical form. We discussed the surprising fact that despite its immense size and stellar population, IC 1101 is, in a cosmic sense, a dying galaxy. Its star formation largely ceased. Its gas supply depleted over eons of consumption. We explored the truly mind-bending scale of its central supermassive black hole, a gravitational monster with tens of billions of solar masses, capable of spaghettifying anything that wanders too close, yet currently in a relatively quiet state, having consumed most of its readily available fuel. We journeyed into the far future, contemplating the inexorable march toward the universe's heat death, where stars burn out, stellar remnants cool into black dwarfs, and even black holes eventually evaporate through Hawking radiation, leaving behind an empty, cold cosmos. And through it all, we touched on the profound implications for our own existence. That we, as conscious beings on a tiny planet, can even begin to comprehend such cosmic majesty. That the very atoms in our bodies were forged in the hearts of ancient stars, connecting us directly to the distant fires of galaxies like IC 1101. That our curiosity to understand these wonders is, in a way, the universe itself being curious about its own nature. When you next look up at the night sky, remember IC 1101. You cannot see it with your naked eyes. It is far too distant and too faint for human vision, but it is there, quietly existing in the direction of the constellation Virgo, shining with the combined light of 100 trillion stars. It has been there for billions of years, and it will remain there for billions more, long after our own sun has burned out, long after Earth has been consumed by an expanding red giant. IC 1101 will still be there, slowly fading into the cosmic night, but not yet entirely gone. We are part of a universe that contains such wonders. We are made of the same stuff as IC 1101 stars, formed by the same processes, governed by the same unchanging laws of physics. In studying that distant giant, we learn about ourselves and our place in the grand, unfolding story of cosmic evolution. The biggest galaxy we have ever discovered is bigger than your imagination. But the fact that you can imagine it at all, that you can hold in your mind a picture of 100 trillion stars spread across millions of light years, that you can wonder about its past, its future, and its potential inhabitants. That is perhaps the most amazing thing of all. Thank you for joining me on this journey through the biggest galaxy ever discovered. If this video helped you see the universe in a new way, please consider leaving a comment, letting us know what you think about our place in a cosmos that contains such wonders. And if you want to keep exploring the mysteries of the universe with us, do not forget to like this video and subscribe to the channel. Until next time, keep looking up and keep wondering. The universe is an infinite source of awe, constantly challenging our perceptions and expanding our understanding. Each new discovery opens another door to greater knowledge, reminding us of the endless possibilities that lie beyond our current grasp. We are privileged to live in a time when such profound insights are accessible, allowing us to connect with the cosmos in ways our ancestors could only dream of. So, carry this sense of wonder with you, letting it illuminate your thoughts as you navigate your own journey through the vast and mysterious tapestry of existence. It's a beautiful thought. It's an amazing universe.